Hi there, and welcome to Raylene Math. In this video on the dot product, we're going to look at projections of one vector onto another in 2 dimensions and orthogonal complements. Let's project a vector b in 2 dimensions onto a vector a. When we project a vector, we're really coming up with the parallel and perpendicular component vectors that can add to give the original red vector. So we're really making a right triangle in the same direction of the ground using the red vector as the hypotenuse. I'm going to call this black vector D, which is perpendicular to A, and the green vector I'm going to call it C, which is parallel or in the same direction as the ground vector. In this way then we get a statement that says vector C plus vector D is equal to vector B. And we can also do the same kind of projection of a vector B that's anti-parallel. Well, vector B is going to the left of the direction of vector A. If we do that, we really need to consider that the ground is extended, and when we extend this ground, we make our resolution triangle to the left. So this is vector C now going anti-parallel to A, and vector D is still going up in this case. So here we have an angle between the two vectors, which we call theta, which may be between 0 and 180 degrees. Okay, so let's take a look at some of the definitions. The vector projection is the C vector. It's the one that is parallel or anti-parallel to the ground vector. And so we're just going to rename that vector projection, or the parallel projection vector, as C. The formula for C then is given by the dot product of A and B divided by the magnitude of A squared multiplied by vector A. In other words, it's the dot product of the two vectors divided by the magnitude of the ground vector multiplied by the ground vector. There's another video in this series that shows the proof of this formula. And another name for this vector C is called proj of B onto A. Now we project onto the ground. A projection is really just a shadow, so it's like we're imagining the sun is casting a shadow, and when the sun tries to pass through the rays of lights through this red vector, the shadow is cast, which is vector C, along the ground. And vector D is just the perpendicular vector which completes the right triangle. In other words, vector D is the orthogonal complement, because complement means to complete, and orthogonal is just another word for perpendicular. Okay, so vector C is really the base vector of this triangle, whether the triangle points in the same direction as vector A or anti-parallel to the vector A. The scalar projection then is called the comp of vector B onto vector A. Unlike proj, which is a vector, comp is a scalar quantity, and it's given by this formula. Now, the meaning of comp is either positive or negative, the magnitude of vector C. So we can take plus or minus the magnitude of vector C, and that's what the comp of B onto A really means or is equal to. The reason it's plus or minus is because vector C could be parallel to vector A or anti-parallel to vector A. And that really depends on whether the angle between the two red and blue vectors is between 0 and 90 degrees. If that's the case, we get positive. The magnitude of C is the comp. So if the angle theta between the two vectors is between 0 and 90 degrees, we get the positive sign here. And if the angle between the two vectors is technically these are not equal to, these are just open brackets. And similarly here, if this is between 90 degrees and 180 degrees, we will get the negative sign. And that's just because the dot product involves a cosine, and this is an angle in quadrant 2, and the cosine of quadrant 2 angles will be negative. Similarly, here we have a quadrant 1 angle, and the cosine of quadrant 1 from the dot product will be positive. Okay, so here this is a scalar quantity, and the meaning of this scalar quantity for the comp is plus or minus the magnitude of that green vector. So I'll just rewrite it again, plus or minus the magnitude of C. So let's take a look at some examples right now before we continue with definitions 3 and 4 and work out the vector projection and the scalar projection. But one more thing. Before we go on, we'll notice that the A dot B over A is built in part into the definition of the proj. So if we divided by another A and multiplied by vector A, we would get turn the comp or the scalar projection into the vector projection. Okay, now in number 3, let's take a look at the definition of orthogonal complements. The word orthogonal means perpendicular, and the word complements means to complete. So when we talk about two complementary angles, those are angles that add up to 90 degrees. If you consider a right triangle with a 90-degree angle, the other two angles add up to 90 degrees. And so those two acute angles are complementary because they complete the right triangle. Similarly, two orthogonal complementary vectors are a base vector C and a height vector D, which are perpendicular and complete the right triangle, with the hypotenuse being the red vector. Here we have some components of vector A called A1 and A2, and we look at the perpendicular vectors. Let's see a picture to compare this first. So we've got the blue line, which can come up with a blue vector. If we go from here, we can go 1, 2, 3, 4, 5 spaces to the right and up 2, and we can create a vector. Let's call that vector A. And vector A has 5 spaces to the right, 2 spaces up, so those are the components. Meanwhile, we know that the slope of that blue line is going to be delta y over delta x, which is 2/5. Similarly, we have a perpendicular line, and from here we can go down 5 spaces and right 2 and create another vector. This vector lies on the perpendicular line, so we know that the slope is equal to -5/2 because we have the negative reciprocal slope. But this means that we have a delta y over delta x, which is opposite to the delta y and delta x we had for the blue line, which means that we are going to swap the horizontal and vertical components to come up with the perpendicular vector. But not only are we going to swap the delta y and delta x, we have to change the sign of one of them. So we could change the sign of the first component, but that would actually mean that we went left 2 spaces and up 5. The other option is that we could come up with +2, -5. So the vector that I've sketched here, A perpendicular, is actually the one with a positive x component and a negative y component, which means that the one that I drew first, or the one that I wrote first, is actually the anti-parallel of A perpendicular. Either way, the black vector or the red vector are both perpendicular to the original blue vector. So if we go back and take a look at these definitions, it says that both A perpendicular and negative A perpendicular are perpendicular to the original, but they are anti-parallel to each other. They're 180 degrees rotated. And so we have the magnitude of all three of these vectors are the same, and it will be equal to the square root of A1 squared plus A2 squared. Furthermore, the slope of a line through vector A and negative A, given by m equal to delta y over delta x, is going to be A2 divided by A1. Meanwhile, the slope of a line perpendicular is going to be the negative reciprocal, as we just said, and so the slope will be negative A1 divided by A2. Now, we could actually see that means the negative belonging to A1, and we have positive for A2, or we could have positive A1 divided by negative A2. And that's how we came up with the two different variations of the black vector and the red vector, depending on whether we went to the left and up, or if we go to the right and down. The word complement, like complementary angles, as we just said, means to complete. And so here these are two vectors that are forming the two legs of the right triangle, completing the right triangle with a hypotenuse of b. And lastly, if we have a vector A, which is given by 3i hat minus 4j hat, we could come up with one perpendicular or complementary orthogonal complement by swapping the x and the y components and changing the sign of one of them. So first off, we could say 4i hat plus 3j hat, or we could come up with the anti-parallel vector to that first blue vector, which is still perpendicular to the given A vector, and we would get negative 4i hat minus 3j hat. Then in number 4, when we want to talk about the orthogonal projection vector, remembering that we had our vector B and we were projecting onto the ground vector of A, that we get a parallel base vector, which we call C, the proj, and we also get this orthogonal complement vector D, which is known as the orthogonal vector when B is projected onto A. So we have a couple ways that we can work out D. As we said earlier, vector C plus vector D is equal to vector B. And so we could actually subtract vector C from both sides, and when we do that, we get an expression that says vector D is equal to vector B minus vector C. So if we know B and we know C, we can work out D. Another way we can consider that is to project vector B not onto vector A, but onto the perpendicular of vector A. And if we do that, the sun is going to shine from a different direction, and we get the projection vector of the red onto the black is going to give us our vector D again. That vector, if we move it over here, we get vector D when we project B onto A perpendicular. Okay, so let's take a look at some examples using these definitions. In exercise 13, we are given two vectors, A and B, and we want to determine the two orthogonal complements of A. So I'm going to use blue for A. Maybe I'll come up with a sketch of these just so that I can visualize these vectors. And if I want to come up with the two orthogonal complements, maybe I do need to be in all four quadrants. So I'll move my x-axis up a little bit. Vector A goes 3 spaces to the left and 1 space up. And so the two vectors that are perpendicular, we can find them by saying A perpendicular. We can swap the components and change the sign of only one of them, giving us positive 1 I hat plus 3 j hat, or the negative of that vector, which will be given by negative I hat minus 3 j hat. We can see then if we imagine this is a line, what we're basically doing is drawing a perpendicular line and rotating that vector in blue 90 degrees so that we're going, instead of over 3 up 1, we're going over 1 up 3. And so we have the same length for this vector or the antiparallel. So I'm just going to put a red tip on the one that's going to the right and up, and I'm going to do a green tip on the antiparallel. Okay, so those are our two orthogonal complement vectors. In part B, we are asked to come up with the scalar projection of B onto C, which is the comp of vector B projected onto vector A, which is given by the dot product of the two vectors divided by the magnitude of the ground vector. The ground vector is the vector in this notation, which is subscript. So it looks like it's lower, it's on the ground. And we can work out the dot product in rectangular form, so we get negative 3 times 2 plus 1 times 1 divided by the magnitude of vector A, which is given by Pythagorean theorem. We could always imagine drawing a right triangle here. We see a base of 3 spaces to the left and 1 up, and therefore the hypotenuse, or the magnitude of the vector, is square root of 10. And so we get negative 6 plus 1 is negative 5 divided by 10, and we could write 10 as 5 times 2, so we could reduce this, and we could have 5 divided by root 5 gives us root 5. So you can either leave it as negative 5 over root 10 or negative root 5 over root 2, depending on whether you want to leave radicals in the denominator or not. You could also multiply by the square root of 10 over it on the top and the bottom to simplify the radical. I'm going to leave it as negative 5 over root 10 though. Okay, what does that actually mean? Remember, we were coming up with a projection vector, and this is the projection vector C, which is going to be the base of a right triangle formed when B is the hypotenuse and A is the base. This is the negative, the magnitude of that vector. Okay, part C says the vector projection, which we call proj, of B onto the ground of A. It's also called that vector C. Now I haven't actually sketched vector B yet, so I will do that now in red. We're going to go 2 spaces to the right and 1 space up. And so that vector B is going to be projected onto A. I'm going to sketch those vectors again over here. Vector B and vector A. So what we're doing is projecting B onto the ground of A so that we can make a right triangle. Now this right triangle is going to be in the opposite direction that the vector A is pointing. We're going to get a base triangle along the ground, and we are going to get the orthogonal complement vector, or the height of that right triangle, which we called vector D. So our goal here in part C is to work out the vector C. And we do that using a dot product again. It's the dot product of the hypotenuse vector and the given ground vector divided by the magnitude of the ground squared and multiplied by the ground vector. It's important to use this verbal notation when talking about this formula, because if this happens to be called B, we'd need to make sure to adjust or swap the A's and the B's. Okay, so let's just work the rest of this out. One thing we can consider is that we've already worked out A dot B divided by A. And if we break this apart in the bottom, we have A times A. So we've already got this A dot B over A in part B, this negative 5 over root 10. So from there, we can continue and say we have negative 5 over root 10 multiplied by 1 over A, that I wrote in red, and then multiplied by the A vector. So we know that A is the magnitude of root 10. And so we get negative 5 over the square root of 10 times 1 over the square root of 10 multiplied by vector A, which was given, and vector A is negative 3I hat plus 1j hat. I'll use the basics vector notation, negative 3I hat plus 1j hat. So this is giving us negative 5 over 10 times negative 3I hat plus j hat, which is going to be negative 1/2 distributed through, or scaling on the vector A. So negative 1/2 times negative 3 is positive 3/2 I hat minus 1/2 j hat. And this is the vector C, which is in green. And so we see that this green vector is indeed going to the right and down. So to the right and down. In part D, it looks like we want to swap it around. We want to come up with the vector projection of B onto A perpendicular. Now there are 2 choices for A perpendicular. It could be that we worked this one out as the negative of A perpendicular, and that one is the positive of A perpendicular. It doesn't really matter which one you choose to be A perpendicular. So I'm going to choose the simpler of the 2 versions for A perpendicular with both positive quantities. So to work out the answer in part D, I think I'll put my working out to the right over here. So we're going to choose the proj of B onto A perpendicular, where B is equal to 2, 1, and A perpendicular was equal to 1, 3. And therefore this quantity is a vector, and it's given by the dot product of A perpendicular and B divided by the magnitude of the ground vector squared multiplied by the ground vector. And we know that the magnitude of A perpendicular is equal to the magnitude of vector A because they're the same vector, just rotated 90 degrees. So this magnitude of vector A perpendicular is root 10, and when we square it, we get 10 in the denominator. The dot product of A perpendicular and B we get by working out 2 times 1 plus 1 times 3, and that gives us a value of 5. And then we multiply by the A perpendicular vector, which I'm now going to write with I hat and j hat notation. And so we end up getting 1/2 I hat plus 3/2 j hat. And then the last part of this question, E, says to work out the orthogonal projection of B onto A. So when we work out the orthogonal projection, use another color here. That's just a fancy way of saying we want to work out vector D, which is the vector that we sketched over here to complete the right triangle formed when B is projected onto the blue ground. So in this case, we can swap this round by, instead of projecting B onto A and coming up with a perpendicular, we can project B onto A perpendicular and come up with the new base. When we do this, we are doing the same calculation that we did in part D up here, which says A perpendicular dot B divided by the magnitude of the ground vector squared multiplied by the ground vector. And so this is indeed 1/2 I hat plus 3/2 j hat that we found in part D. But this vector is nothing more than the vector D we found over here, which is going to the right and up. So those are all different examples of the scalar and vector and orthogonal projections and orthogonal complements of two vectors. We can skip ahead now to exercise 15, which is an application of using the orthogonal complement to find the minimum distance between a point and a line. So in this exercise, we are asked to find the distance or the minimum distance between a point and a line. When we do talk about a line and a point, it should be noted that there's an infinite number of distances because there's an infinite number of points on the black line. If we were to simply say to find the distance between the point and the line, we'd be looking for the minimum distance, which we would be finding on a perpendicular line intersecting. And then this blue distance between point A and point B is the minimum distance. Now, we could use some Cartesian coordinate geometry to work out the minimum distance. We could find be given the equation of the black line and find the equation of the blue line as a perpendicular line passing through point B. Then we could find the intersection of those two lines to get point A. Then we could use distance formula. So we should be trying that method to compare with the vector projection method we're going to see now. So what we want to do is first of all recognize we are coming up with some vectors, and I'm going to make this a little bit bigger so that we can see the graph a little bit better. And there, we'll do it one more time. So we've got a point, I'm going to call that point P, and the coordinates of point P are given as 4, 1. And we are really looking to come up with this minimum distance. We're going to do that by creating vectors. The vector that we're going to do, first of all, we're going to choose some points. We're going to come up with a vector on the ground, and that's going to be our ground vector, vector A. So I'm going to choose any point I like on the line that's given, and I'm going to go to any other point that I like. And I like this point over here. So I'm going to make a vector from this initial point, which is 0, -1, to this point down here, which is -2, -5. And that's going to give me my vector A. So I can find vector A as delta x, delta y from those 2 points, which is going to be 2 spaces to the left and down 4 spaces. Now, it should be noted that I could have chosen any other point I wanted on the line, or any 2 points on the line, and come up with any vector A. It doesn't matter which 2 points you choose, it will always work. Okay, going back to the vector that I've chosen then, the next thing I want to do is to come up with a vector B. Once I've identified a start vector, or a start point, I'm going to use that point to come up with my vector B in red. And so vector B is going to be the delta x and delta y from its start to end points. The end point is given as 4, 1. And so the delta x is going to be 4, and the delta y is going to be a rise or an increase of 2. Really what we're talking about then is to project the red vector onto the blue ground. In this case, my A vector is in the opposite direction of my projection triangle, and I can see my C vector along here, and I can see the orthogonal complement that completes that vector along here. Really, the minimum distance I'm looking for is the magnitude of vector d. And I know that vector d is the orthogonal projection of B onto A, or the regular parallel projection of B onto A perpendicular. So now I need to work out A perpendicular vector, which is going to be a swap of the delta x and delta y components and a change of sign of only one component. This, remember, is like finding the slope of a line to be 2/3 and then the slope of a perpendicular line to be negative 3 over positive 2, or positive 3 divided by negative 2. You only change one sign of the delta y or the delta x. So I'm going to swap the two components and change the sign of the first term. So that gives me a perpendicular vector of 4, negative 2. So if I take my start point and I go 4 to the right, 1, 2, 3, 4, and I go 2 down, that gives me my A perpendicular vector, which would be on a perpendicular line to the original line. Those two lines are perpendicular because their slopes would be negative reciprocals. Now I'm going to project vector B onto vector A perpendicular and come up with the triangle, the complementary vector triangle. In other words, my vector D is going to be the orth of B onto A, which is going to be the proj of B onto A perpendicular. And so if I do this proj, I'm going to get A perpendicular dot B over the magnitude of A perpendicular squared multiplied by the ground vector. But that's going to give me the whole vector. And I only want the length of that vector to come up with the minimum distance between the point P and the given line. So I really need to come up with the comp of B onto A perpendicular, which, if you remember, is just this part of the proj formula. So I'm going to do the dot product of the two vectors divided by the magnitude of the ground vector. Remember that this comp could be plus or minus depending on whether the angle between the two vectors is acute, less than 90 degrees, or obtuse, more than 90 degrees. And so in the end, to get distance, I may have to take the absolute value to make sure that I get a positive answer for distance. It depends really on which choice of A perpendicular you have. We could have had 4, negative 2 or negative 4, positive 2. If I had chosen a different A perpendicular, I would have had an angle that was obtuse, and my dot product would be negative, and then I would have to take the absolute value to get the distance that I'm looking for. The choice that I happened to make, coincidentally, made the angle between A perpendicular and vector B less than 90 degrees, so my dot product will be positive, and I don't have to take the absolute value. Okay, let's finish off the question. The dot product of A perpendicular and B, we multiply the product of the x's and the product of the y's, and we add them together. So we're going to get 16 minus 4, which is 12, and divided by the magnitude of vector A, which is the square root of negative 4 all squared plus 2 squared. So we get 12 divided by the square root of 20, and the square root of 20 can be simplified as 2 times the square root of 5, and then 12 divided by 2 reduces to 6. And so we end up getting that the minimum distance of that black vector, or the length of that black vector, is 6 over square root of 5 units. And there you have it, some applications of projections and orthogonal complements of the dot product. That's all for now.